and I would also like to thank AIT and the whole team for the wonderful invitation. I've never been to Thailand before, and this has been an amazing visit so far. So I'm going to talk a little bit about my background and how I ended up here. I started training in 1995 as a structural engineer at Trinity College Dublin. Trinity College Dublin is one of the oldest schools of civil engineering in Europe. I had a very traditional engineer's education. I could do lots of math, but I didn't know what any of it was for. And so I then went to graduate school, and I went to work with this man. His name is David Billington, and David Billington worked at Princeton for many years, and he developed a reputation as an extraordinary engineering educator. And he was really, really invested in the idea that we understand the humanity of engineering, that it was in the service of human beings, that it was done by human beings, and that no piece of structural engineering existed without its political context, its economic context, the physical context in which it lived, and that engineers ought to be trained to understand these things, to debate these things, to measure projects based on these measures. And so he's written a series of quite influential books, and one of them, The Tower and the Bridge, was mentioned earlier. And I began to teach alongside him in a series of quite innovative courses. And in doing so, I suddenly learned that all of this math that I had been learning had a purpose and had a kind of an involvement with the physical world that I hadn't fully appreciated. And I started to learn the history of my discipline, the history of men like Gustav Eiffel, this is one of his bridges, and of course the Eiffel Tower, the bridges of somebody like Robert Mayer, who was working in the Swiss countryside but was developing incredibly innovative forms in a new material, reinforced concrete, in the early part of the 1900s. He is followed on very much in the same tradition of Swiss engineers by somebody like Christian Menn, working in the 80s to the modern day in long-spanning pre-stressed concrete bridges, the shell structures of somebody like Pier Luigi Nervi, or Felix Candela, working largely in Mexico. Of course, when we look at tall buildings, we've talked a lot about tall buildings here this morning, the legendary partnership at SOM of Fosler Kahn and Bruce Graham, really developing the beginning of what we now consider to be the tall building designs, sort of tubes and bundled tubes that are still largely the strategy that we use to build tall buildings today. And none of this had been taught to me as a structural engineer. Not a single, I had never heard of these people, I had never heard of these words, I had never connected all of the math that I had learned to real things in the real world, and this was just a revelation to me, and I decided that I wanted to teach. This is, of course, the Hancock Building in Chicago. This is another Fosler Kahn and Bruce Graham project. And so I got a job working at a school of architecture, not a college of engineering. And so everywhere I go, I have to start with, I'm not an architect, because I spend most of my time dealing with architecture students, and I teach a few engineering students on the side. And I started a research project with a colleague of mine, Claire Olson. And this is the book that we ultimately wrote. But the project started out as a study into education. We were looking at the way in which engineers are taught and the way in which architects are taught. Now, no one in this room is surprised that those are different, okay? But a lot of people who don't know our professions are very surprised when they discover how different they are. So engineering has always been a discipline that values creativity, innovation, that has there's a great quote, and it gets attributed to a whole bunch of different people, so I never want to say who said it, but a lot of universities teach engineering as though it's an applied science. The scientists did the discovering, and the engineers apply the science, and they make the things. That is not really how it has worked. Throughout the history of engineering, the need to provide an engineering solution has driven scientific discovery, not the other way around. And scientists are chiefly engaged with studying that which is already there. Engineers are engaged with making that which was never there. And those are two fundamentally different things. And so engineers have always made, they have always created, but engineering education hasn't always been careful to identify how to do that well and how to foster that. And so that was what we wanted to do. Architecture is very preoccupied with the idea that they make things. and they think very carefully about how to teach their students to make those things. And so we set out to try and investigate what the differences between the two modes were and what we could learn. And one of the things my colleague and I did was we taught a class together. We put some engineering students, some architecture students, and we assigned them a series of projects. And we decided to use shell structures. And the reason we decided to use shell structures is that's what I had written my PhD on, and my colleague, who was an architect, really liked curvy forms. She thought they were cool. And the really interesting thing about a shell is the thing you look at, the thing that keeps the rain out, and the thing that stops the building from falling down are all the same thing. So they were a very useful tool. The class wasn't really about shell structures. They just made a really good example on how to teach architects and engineers together. And so we assigned them a series of design projects. We made them study the history. We made them look at people who worked in these in-between architecture, people who were trained as architects but mostly worked as engineers, or trained as an engineer but did a lot of architectural work over the course of their careers. And we had this group of students, and this is an engineer and an architect. And when we were finished with them at the end of the semester, the team from the School of Education watched these two girls present, and they couldn't tell which one was the architecture student and which one was the engineering student. So we figured we had done a good job. We assigned them a series of, this is some of the work they did, I'm just going to go through it real quick. It's very, very cold in Syracuse, and so we were able to use the principles that Gaudi has used and other people have used, where if you take a form and hang it in pure tension and invert the form, and so we freeze it, this is Matthew and Katie, and you freeze it and you flip it upside down, you get a form that works in pure compression, which for concrete is a great shape. And so we gave them every single assignment had both a technical constraint and an aesthetic constraint, and they had to work together, and they had a formal review just like architecture students have. We invited a panel of distinguished guests. And then they did a final design where they had a client. It was the local train station in Syracuse. They had a series of constraints that weren't just mathematical. And this is some of the work those students produced. And so as we started to present this work in different conferences, we got asked to write a book. And our publisher wanted us to write a book about the collaboration between architects and engineers. So we said sure, because we were both tenure-track professors at Syracuse University at the time, and we really, really wanted to keep our jobs. So we decided we would write this book. And so we set out to think about what people thought of as the difference between an architect and an engineer. Now, if you do a Google image search for, which one is that? Architect, that's what you get. I haven't done this in a while, it might have changed, but that's roughly what you get. Drawings, hard hats, some people. Now, if you do a Google search for structural engineer, you get pretty much the same thing. Hard hats, drawings, some people. Mostly male people both times, but what are you going to do? I'm working on it. Now, if you go back far enough, this is not surprising, because if you go back far enough, an architect and a structural engineer were the same person. You go back to the era of the great Gothic cathedrals in Europe, the person who figured out how to make sure the building didn't fall down, why the building kept the rain out, why the building looked in a particular way, made you feel a particular way when you walked in the door, acted as an icon for your city, that was the same person. That's not true anymore. It's not true anymore for a couple of very good reasons. These buildings took generations to build. Sometimes they fell down halfway through, and guess what? It's not that warm inside. And we're not okay with that. We have much, much higher demands for how quickly we construct things, the cost of constructing things, and the kinds of thermal comfort and environmental performances that we expect them to have. So our disciplines have disaggregated all of those roles and all of those tasks into a whole series of professions, not just architects and structural engineers, mechanical engineers, facade consultants, interior designers, landscape, and so forth and so on. And we train those groups very, very differently. But broadly, we were thinking about those who were trained as engineers and those who were trained as architects. So to give you an idea of the challenge that we wanted to try to explain, these are two classrooms. So on this side, let me see if I can make this. Yeah. On the left are my students, my engineering students. Now my engineering students, this is a statics class, second year engineering. They're learning basic vector problems. They are all doing the same thing. They're all facing the same way. They're all listening to me. They're all doing exactly what I told them. They're all going to solve the problem exactly the same way. And if they don't get the same answer, we're going to have a problem. On the right are my friend Claire's architecture students. She deserted me halfway through this project and got a fancy new job in California, and she teaches now at Cal Poly San Luis Obispo. And these are her students. They are not doing the same things. They've all been assigned the same problem, but they are not working on the same thing. None of them is facing the same direction. None of them is listening to what she's told them to do. They're all going to attack the problem using different methods and different steps. And if they all get the same answer, there's going to be a problem. Now, these are two very, very different approaches to how we teach. And I know some of you are sitting there and saying, well, yeah, because they're in charge of what the building looks like, and I have to make sure it doesn't fall down. Those are two different jobs. But these two groups of people are going to have to work together. They are going to be the groups of people responsible for integrating each of these problems. And if an architecture student knows nothing about how to make sure a building doesn't fall down, and an engineering student knows nothing about what the client might need, about what the spatial constraints might be, about what all the other elements that an architect takes into account are, they're not going to do a very good job talking to one another. And so we set out to write the book with that in mind. We interviewed a whole bunch of people. These are the offices for various architects and engineers that we talked to. These are the locations of the projects. We had about 10 projects. They ranged in scale from very small to very large infrastructural projects. And the idea was to try to talk to an architect and an engineer, whoever we could get to talk to us, for each project, and to ask them about the nature of their working relationship, how that working relationship influenced the final product, and what, if any, advice they had for those both young architecture and engineering students themselves, but also those who were training those engineering and architecture students. So we set out to talk to a whole bunch of people. So this is one of the first projects. It was the Glass Pavilion. It's a relatively small project at a museum in Toledo. And I'm going to show you a whole bunch of images. I'm not going to talk very much. I'm going to go through them pretty quickly. Because the point, again, much like the shell structures in our class, the point is not the structures themselves, but the big picture themes that emerged as we had these conversations with the engineers and architects. So this was a small glass pavilion at a larger museum. It turns out Toledo, Ohio made a lot of glass in the early industrial period in America. And so they have, at their Museum of Art, a very large glass collection, and they wanted a nice building in which to hold it. And they hired the Japanese firm of Sana to design this building for them. And this is some of the other work by that same architectural firm. They're very concerned with the relationship between the interior and the exterior, and they have a high, high degree of control over that particular envelope. That was really important to them. And this is the engineer that worked with them. This is some of his other work in collaboration with a different architect, Toyo Ito. And Mitsuru Suzaki is the engineer involved in this project, and he is also somebody who works very closely with architects and is somebody who's considered a very sort of architect-friendly engineer almost. So there were a couple of aesthetic constraints here that led to engineering problems or engineering challenges. The first is this very thin strip of white that you see at the top of this building. This building looks as though there are walls of glass that hold up this very thin strip of white. And in order to do that, this has to be engineered like a watch. Every single piece has a job to do, and every time you move it, you create a new problem. And so the fascinating thing about this is when we talked to the engineer wanted to tell us about this aesthetic and how much work they did to make sure the aesthetic came through. And when we talked to the architect wanted to tell us about the cool engineering he learned while learning how to achieve this aesthetic. And this was something that was echoed. So you see this very, very thin strip of white. The other goal here was to hide the columns. The building needs to look as though the glass walls hold up the roof. Everyone in this room knows the glass walls don't actually hold up the roof. And so I defy you to find the columns. They're there. There's a column in this photograph. It's hard to see, but it's there. There's one not the one holding up the porch, but there is another column in here. It's hard to see, but it's there. The other big constraint in this building was the thermal conditions. There was a glass-making shop in this building, and so the thermal conditions had to be very carefully controlled because some of the art also couldn't be at very, very high temperatures. And so every single time one of these spaces moved, all of the columns had to move. There's a very careful set of engineering done here to make sure the columns are 3.5 inches thick of solid steel. And they are, in order to make that work, they have to have very few lateral loads, and they have to be isolated from the roof. So there's a series of engineering moves made to make this work. The second major issue for the engineering was to jam all of those mechanical systems and all of the structural systems into as thin a layer as possible to pull off that very thin white stripe that we saw at the start. And so as we talked to the engineer and the architect, they told us the various engineering solutions, and this group of people could very easily understand them, but the book we were writing was for students. They talked us through the various design processes and methods and many of the things that we've heard today. In fact, our last speaker spoke about the importance of having engineers and architects work together right from the start, and that was a major theme that emerged from the conversations we had with the working professionals. And these are just some more images. Another major theme that emerged was lifelong relationships that people built up over time. This is a project for a residential hall at MIT built by the architect Stephen Hall. And the architect Stephen Hall works very closely with the engineer Guy Nordenson, and they have worked together for decades. They know each other very well. They don't work in the same firm, but their firms work together on almost every single project that that particular architectural practice does. And to the point that they've worked together so long now that this was Stephen Hall's first drawing for this project, but this is the engineer's design. This is a precast concrete system suggested entirely by the engineer, designed by the engineer, designed almost entirely on engineering principles, because the level of trust that has built up between the two allows that creativity to be inspired. And so I'm not going to speak in great detail about the project. I'm just going to show you loads of great pictures. This is actually Guy Nordenson, the engineer. And so this is another one of those systems that, because instead of drawing the pretty picture and then coming to the engineer 6 months later and saying, figure out how to make this stand up, the conversation happened right at the start. And so the system that is what you're looking at, that is the architectural scheme, as it were, is also the structural scheme. It's also the big, thick piece of concrete which helps maintain the thermal comfort of this building in harsh winters in Boston and pretty warm summers, not as warm as Thailand, but pretty warm. So they talked us through the process by which this load-bearing facade would change every single time the architect made a change to the sort of makeup or the massing of the project, but that it was tracked through a series of computer models that created these sort of heat maps that showed where the stress is built up. And as you might imagine, in the parts of this building where this Virundel truss-like system is having to be a bit bridge-like, you see higher stresses. Where it's trying to work around the openings, you see higher stresses. And ultimately, as this building was being built, one of the engineers, that's actually a former student of mine, Rebecca, who coincidentally happens to work for Guy Nordenson, was keeping track of the different stresses in this system, because all of the pieces were precast pieces, and they were exactly the same size on the outside, but as this group would imagine, the rebar changes throughout the building as the stresses are higher and lower. And so this is them being built. They were built in a factory in Canada, and the rebar constraints were different. In fact, there was the same number of rebar, but the size of the rebar changed depending on the needs of that particular module. And in order to keep track of all of that, that same engineer that I showed you maintained a spreadsheet. And she color-coded her spreadsheet, with red being the highest stress, as any good engineer, red, danger, high stress, all the way back to green for not so much stress. That can be the small bars, they'll be fine. And one day the architects were happening by and they really liked her spreadsheet, so they painted it on the front of the building. And so all of the colors in the window wells are actually a map of the stress in this building. That's her again. And so we talked through a series of these kinds of issues, and I'm going to go very, very quickly through some of the rest of the projects and just wrap up some of the big major takeaways that we got from the research, because I know there's a break coming and you've all been paying very good attention since your lunch. So this is a project for the Cooper Union, which is a university in Lower Manhattan. And this building is biomorphosis, and this is the kind of building my architecture students love. They love a building that looks complicated and like it's got all sorts of tricks and gymnastics, and it's just fabulous. And so this is built by Morphosis, and this is some of their earlier work. And the engineers who worked with them on this were JAMA, John A. Martin and Associates, and this is some of the previous projects that they had worked on. So big scale, prominent projects. These are fairly prominent engineers and architects. This is actually a previous project by the mechanical engineers for this project. We were very lucky the mechanical engineers also wanted to talk to us on this project. In fact, actually the mechanical engineers are all former Arup engineers on this project. So this is the design, and this is the kind of thing architecture students bring to me all the time. They're like, look at my fabulous design, help me figure out how to make it. And they see this and they think, columns this way and that way and diagonals and no straight lines. I don't believe in straight lines. How dare you talk about gravity, Professor McNamara, and say that it is perpendicular to the ground. No, no straight lines, no perpendicular lines. And so it was really fun actually to talk to both the engineer and architect on this project and see just how much the engineer had to say on this project. So first person we talked to was a guy called Kurt Clandening, and he was the architect of record on this, or not the architect of record, but he was the senior architect for Morphosis on the project. And he said, well, so day one, we're in the meeting with the engineers, and they tell us this building has to be built out of concrete. And he gave us like a whole big engineering rationale for why this building had to be built out of concrete. And so right from the start, the engineers were having a huge influence on how this design evolved. This is also one of the architect's early sketches. But if you break this building open, you start to see it's actually quite normative, right? It's a 30 by 30 foot, 10 meter by 10 meter column grid. It's fairly regular, and it's only in the places where you're going to see the crazy that we actually do the crazy. And this is a huge lesson for my architecture students to learn. And one of those moves is this corner, this bottom corner. There's no column, and they want to open up that corner. And when we talked to the engineer, one of the lessons that he taught us was that many of the people in his firm would have told the architect no when they wanted to take 7 or 8 stories of weight as a point load and put it on the end of a cantilever. All his colleagues said, tell them no. Tell them they can't do it. Tell them they can paint the column white or they can do something, but no, they have to have the column. But this engineer was like, no, I need to listen to the architect. I understand. He had listened to their project, their plans, what they wanted from the project, and figured out how to make it happen. And basically, I think I have it as, so here's that corner, and here's the solution. So what they did was they took, I'm going to see if I can make this work. Yeah. Okay. All of my engineering degrees, and I cannot make this do. Let me try that. So what you see on the end here is a large point load coming onto a cantilever, so naturally the bending is... Okay, so you've got a very large point load here, so you have a very long cantilever. Now you fix that very long cantilever in 2 ways. The first is instead of having a column here, you incline the column out a little bit, minimize your span a small bit, and then you have to have a huge depth. And rather than having the huge depth come down here like a beam, he flipped it upside down and made it a wall. Because all of these are labs, but this was faculty offices. And so they figured they could get away with having a smaller window in faculty offices. As everybody knows, faculty are the least important people at any educational institution. Okay. And so similarly, I would expect when my architecture students come to me, they see this and they think this is a continuation of that column. It's not. That's faked. And so this was a great project where I myself am a big proponent of architecture that wears its structure consciously, the ones where it's very structurally expressive and you can see it. But a lot of architecture today doesn't do that. A lot of architecture, what you're looking at and how a building stands up are very, very much divorced. And this was a nice kind of mediation between the two, where yes, you're seeing some sort of unusual, non-regular structural gymnastics, but where it makes sense to do the regular thing and then just have the facade take care of that appearance, that's the choice that they made. So there's a kind of nice balance between some of the constraints that happen on typical projects. We also had looked at a much larger infrastructural project by Schleich, Bergermann and Partner, who are German engineers working with the architecture firm von Gerken, Marg and Partners. And this is some of their previous work. So you can see they're well-versed in infrastructural scale work. And this is a huge piece of the city of Berlin. After the reunification of Germany, they had to knit the city of Berlin back together because they had been separate for 30 or 40 years. I think actually we just passed the point where Berlin has been back together now, longer than it was ever separate. And so the whole building is a big stitch. It's like you're sewing the city back together with a big stitch. And here, it was really interesting to talk with the engineers who talked about this big glass roof and how all of the design for this is based on engineering principles because of the scale. Because they wanted a measure of transparency and the scale was very, very large. I think I have an image of the scale of this. So, because they wanted to have complete transparency and because the scale was so big, the form had to be derived from the engineering principles. And so what you see here, and anyone in the room who's a structural engineer will see, that is a fixed bending moment diagram. And you have tension members on the tension on the top, compression on the bottom, compression on the top, tension on the bottom, and so on. And Hans Schober, who's one of the senior engineers for Schleich Bergman and Partner, describes this quite beautifully as dissolving the structure into its components. Struts for the compression and ties for the tension. With the result that even though this spans 66 meters, the thickness of the structural member as it reads to a member of the public is 13 centimeters. And Schleich is known for the accuracy of their detailing work. Okay, I'm actually going to skip this project in the interest of time. This was an SOM competition project where we looked at their method of in-house collaboration and how successful that's been for them over time. And so there were, like I said, there were about another 7 or 8 projects that we looked at, so we had some takeaways in the book. The first was vocabulary. Designers and architects have a set of words, a language that they use to describe their projects, and engineers, we have a technical vocabulary, and the two do not overlap very, very well. In particular, we noticed it when we were teaching the class, and this was an example that my colleague drew up. The very first assignment we gave them was to make 5 shells, and we told them a parabola was a strong shape. We said, okay, parabolas are good shapes, make 5 shells. And we just sort of let them off, and we gave them some paper and some pins and some boards. And right as they're leaving the room, my colleague Claire says, make sure to differentiate the spaces. And the architecture students all went, yeah, sure. And they wrote that down. And the engineers were like, what do you mean? And I looked at my engineering students and I said, okay, how many calculus classes have you taken? And they had taken 1 or 2 or 3 calculus classes. And I said, you mean to tell me there's no one here who has a definition of the word differentiation? And they eventually said, well, dy dx. And I said, yeah, well, what does that mean? What's it for? And I was reminded of me at the end of my years as an engineering student where I could do all this math, but I didn't know what any of it was for. And eventually, I kept pushing and eventually I got someone to say the word change. And of course, as everyone here knows, calculus is the rate, differentiation is the rate of change of one parameter with respect to another parameter. And I said, okay, in architecture, it means exactly the same thing. It just might be a bit looser. It's not volume with respect to time or distance with respect to time, also known as speed. Right? It's maybe the shape as you go along the object, or maybe it's the height as you differentiate the 3 pieces from each other, so forth and so on. So we had a really good time teaching the students how to learn to talk to each other, right? Because it's not like there's a list of words that I as an engineering professor can teach my students about that architects use, or that I can teach my architecture students that engineers use. But what I can do is teach them how to foster that communication amongst themselves so that every time that happens, they have tools with which to learn to both advocate their own position but understand somebody else's position. Another big takeaway for us was the incredible mutual respect with which everyone we spoke to talked about their team members. And this is not always thought of as standard. There's often a kind of, I think on construction sites in particular, there's often a kind of, we love to be like, oh, those architects. Or, you know, and architects love to tell me about the engineer who ruined their project with the columns by putting columns everywhere. I don't know what architects' problem is with columns. They don't like them. But actually, when you looked at the best examples of these projects, these people who had worked so closely together had tremendous respect for each other's knowledge and tremendous capacity to understand where their own knowledge stopped and where they would need to look for someone else's knowledge. I think that's a great lesson for any student of either of those disciplines. Oh. The other thing we really noticed was a degree of mutual learning. It was fascinating to me. I was speaking about the vocabulary issue just a second ago. It was fascinating to me as someone who has worked now in architecture for 11 years, and I've learned a little bit of the lingo. It was fascinating for me to hear engineers talk and use words that I know they learned from an architect, and vice versa. To hear an architect talk to me all excited about the depth of the structural beams because of where the shear was high. And you know they learned that from one of their engineering partners. And that, I think, really speaks to the kind of lifelong relationships that engineers and architects develop over time, either with a specific individual that they work with again and again, or just with the discipline more generally. And I think that's another great lesson for architecture and engineering students to learn, because as we've seen this morning, both professions evolve. They're evolving rapidly, and they're evolving to meet challenges that were inconceivable 25 years ago, 50 years ago. And yet, if you look at the start of most engineering textbooks, they're 50, 60, and 70 years old. The textbook that I teach statics from at Syracuse University was first published in 1947. Statics has not changed. But as we heard earlier, the degree of rapid urbanization, the incredible pace of technological change in the meantime means that our students are going to face challenges in the practice that I haven't thought of yet. And so we have to equip them for the kind of lifelong learning and lifelong relationship building that will make them be successful in these endeavors. Engineering students have to engage with their history. When I teach engineering, I teach it through the lens of a series of historical examples. Nobody in a school of architecture was surprised when I do that. But when I try to do it in an engineering curriculum, people think I'm teaching the soft class, the easy class that doesn't have as much math in it. Time and time again, when there is a major engineering failure, it is not because of a brand new problem. When footbridges and when bridges vibrate, people need to be reminded that Thomas Telford observed those vibrations when building the first suspension bridge in 1806. That the Romans had observed those vibrations when they marched their soldiers over bridges and very quickly learned that you don't march an army in formation across a bridge. When we have the kinds of earthquake collapses, some of the other things we've seen here today, they are almost never because of a new problem. They are almost always because somebody failed to learn the history of engineering. And the last, I think, takeaway that we came, I think, very much touches on some other points that were made earlier today, which is that engineers and engineering students need to engage with visual culture. Now, that's my definition. I've just come up with that. What I mean by visual culture is real objects in the real world, photographs of those objects, drawings of those objects, sketches. Learning to understand that the sketch is the language of communication between an architect and an engineer, between an engineer and a construction manager, between an engineer and a fabricator, between a construction manager and the shop, and the workers who actually have to, a rebar schedule, all these things. These are the modes of communication. And in some cases, they are the legal documents that are referred to if there's a problem later down the line. And I have engineering students who will not put a pencil to paper and draw a straight line, even with a ruler. They think that drawing is a talent that you are born with, not a skill you can learn. And it is, and it is a skill that nobody, I think very few people are in fact born able to both draw and read a drawing. And it is one that we must critically must develop in our students, because it leaves them, it's like we've taught them we've taught them engineering in English, and then we've sent them to a construction site where everybody speaks Thai. This is not going to go well. So that's the last, I think, of my slides. This is another example of what I meant by engaging with visual culture, understanding the ways in which the physical objects are related to the mathematics is often far more easy to understand if you draw it than if you do the math. And so both of these last two examples are structures that are their bending moment diagrams. And I like them because, as I said at the start of the talk, I left engineering school able to draw much more complicated bending moment diagrams than that. The ones that took forever, that had a hinge and an applied moment and 45 other stupid things that never exist in the real world. But I couldn't have told you what any was for. I didn't know that the Eiffel Tower was a bending moment diagram. I certainly wouldn't have recognized this bridge as a bending moment diagram.